Our objectives in this lesson are the following. Define population proportion and sample proportion. Determine the value of the population proportion and sample proportion. Identify appropriate test statistic when central limit theorem is to be used. And apply population proportion in real-life situations. Let's have an activity. Let us analyze. In ABC Senior High School, 48% are grade 12 students. The coordinator conducted a survey to determine how many students will pursue tertiary education. She randomly selected 100 grade 12 students, and 88 said they would enroll in college. Number 1. What is the survey all about? The survey is all about grade 12 students who will pursue to college. Number 2. What percent of the senior high school is grade 12? Answer is 48%. Number 3. How many grade 12 students were surveyed? It says here, she randomly selected 100 grade 12 students. Number 4. How many grade 12 students will enroll to college? 88 said they would enroll in college. Number 5. What variable describes the population? So what is the variable in our population? It is ABC Senior High School students. That is the population here. And what variable describes the sample? This sample, grade 12 is student. Let us dig deeper. In the question, what variable describes the population, we answered ABC Senior High School students. And in the question, what percent of the senior high school is grade 12, we answered 48. This 48 is a part or a portion of the senior high school students. And this is what we call population proportion. Population proportion is denoted by a small letter p. It is the portion of the population with common characteristic. It is a fixed value. In our example earlier, what percent of the senior high school is grade 12? The answer is 48%. This will not change. It is fixed that the portion of grade 12 students in the senior high school is 48%. To convert this to decimal, let us move 2 places going to the left. Decimal point will be here. So this is equal to 0.48. In formula, proportion is the number of elements in the population with common characteristic divided by the number of elements in the population. If we are going to denote letter x for the numerator, this will be p is equal to x over n, where capital N here is the number of elements in the population. Let us go back to our example earlier. In the question, what variable describes the sample, we answered grade 12 student. How many grade 12 students were surveyed? We answered 100. And how many grade 12 students will enroll to college? We answered 88. What we can get from these details is what we call sample proportion. Sample proportion, denoted by this symbol, which is read as p hat, is the best point estimate of the population proportion. It is a random variable because it was obtained from random process. It may or may not be equal to population proportion. In formula, it is the number of elements in the sample with common characteristic divided by the number of elements in the sample. The numerator is usually denoted by a small letter x, so this will be p hat is equal to x over n. X here is referred to as number of successes, and as we all know, n is the sample size. So in our example, how many grade 12 students were surveyed? 100. How many grade 12 students will enroll to college? 88. Our sample here is the grade 12 students. And from there, you randomly selected 100 students. Your question is if they will enroll to college. And 88 answered yes. This is what we considered the success. So P hat would be equal to 88 over 100. And this is equivalent to 0.88. Let's have an activity identifying proportions. Identify the population and sample proportions on each of the following situations. In a particular ATM branch, 65% are just checking their available balance. 120 people were randomly selected and 78 confirmed that they had just checked their account balance. Let us solve for the population proportion. Let us recall the formula. This is the common characteristic divided by the total number of population. But in this situation, we are already given the population proportion, and it is 65%. In decimal, this would be 1 to 0.65. Now, let us solve for the sample proportion. The formula again is P hat is equal to X over N, where X is the number of successes and N is the sample size. Let us identify first the sample size. 120 people were randomly selected. So this is our N, 120. And 78 out of 120 confirmed that they had just checked their account balance. That would be our X. So we have 78 over 120, and this is equal to 0.65. This is an example wherein the population proportion is equal to sample proportion. But I tell you, it is not always the case. Let's have another one. From a total of 68 teachers in a particular school, 57 attended a webinar. 88% of the teachers randomly selected said they would try the new application they have learned from the webinar. Let us solve first for the population proportion. It says here from the total of 68 teachers. So this is our population. And the common characteristic is attended a webinar. So the formula P is equal to capital X over N. N is our population. That would be 68. The common characteristic, again, is that 57 attended the webinar. So this will be 57 over 68. And this is equal to 0.84. Now, for the sample proportion, our formula again is P hat equals small letter x over small letter n. But in this situation, we are already given the sample proportion. It says here, 88% of the teachers randomly selected. So meaning this value, this proportion comes from the sample. So this is our P hat. This will be 1 to 0.88. Sometimes the sample proportion is already given. Sometimes you have to compute for it. Let's have another one. An online seller claims that 95% of all orders are shipped within a day. A group of consumers placed 250 orders and 210 were shipped within the day. For the population proportion, let us assume that the claim of the online seller is valid. So our population proportion is 95%. This is 1 to 0.95. For the sample proportion, again the formula is P hat is equal to X over N. N is the sample size. A group of consumer placed 250 orders. This will be our sample size. And 210 that were shipped within the day will be the number of successes. So we have 210 over 250. 210 divided by 250 will give us 0.84. Now that you already know how to compute for the population and sample proportion, let us discuss the following conditions for estimating population proportion. Number 1, the sample is a simple random sample. Number 2, the conditions for the binomial distribution are satisfied. To determine if it is satisfied, we have to meet these 4 conditions here. Let me give you an example. Let us say you are going to toss a coin for 10 times. So number one condition for binomial distribution, there is a fixed number of trials. I said earlier, you're going to toss a coin for 10 times. So 10 is the number of trials, and that is fixed. Number two, the trials are independent. When you toss the coin for the first time, the result of it will not affect the result of the other tosses, meaning the trials are independent. There is no way for the result of one trial will affect the result of the other trials. Third one, there are two categories of outcomes. When you toss a coin, it's either you will get a head or a tail. Two categories. And last one, the probabilities remain constant for each trial. When you toss a coin, the probability of getting a head is 50%. And that remains constant for the rest of the trials. I hope that this number 2 is clear to you. Number 3, there are at least 5 successes and 5 failures. In formula, NP is greater than or equal to 5 and NQ is greater than or equal to 5. P here is the success and Q is the failure. NQ is equal to 1 minus P. This third condition will be our basis to determine if the sample size is sufficiently large or not. Whenever we hear the phrase sufficiently large, the idea of central limit theorem comes to our mind. In our previous lesson, we say that if n is greater than or equal to 30, then the sample is sufficiently large. But we are not going to follow that condition in population proportion. Now, we have to satisfy these conditions. Let me show you. Using CLT in testing population proportion, 500 Medici students were randomly selected. 77 were left-handed. Is this significantly lower than the proportion of all Filipinos who are left-handed, which is 0.12? Before I determine if the sample size is sufficiently large or not, let us check first if it meets all the conditions. Number 1, the sample size is a simple random sample. It says here is students were randomly selected. Number 1, check. Number 2, the conditions for the binomial distribution are satisfied. One of that is there is a fixed number of trials. We have 500 students. This is our sample size. This is our number of trials. And this is a fixed number. Next, the trials are independent. The answer whether a student is left-handed or not will not affect the answer of other students in the trials. Therefore, the trials are independent. There are two categories of outcomes. It's either the student is left-handed or not. And last one, the probabilities remain constant for each trial. The probability of getting an answer that a student is left-handed, which is 50%, remains the same for the rest of the 500 students. So, the probability remains constant for each trial. Now, let us determine if our sample is sufficiently large. Let us do this. First, let us determine our population proportion, which is already given here. The proportion of all Filipinos who are left-handed is 0.12. Next, let us solve for our Q, and that is 1 minus P. So this will be 1 minus 0.12, and that is 0.88. Next, let us determine our n, and that is 500. Now, let us solve for NP. Our n is 500, our p is 0.12. Multiply them, and it will give us 60. And this is greater than 5. Next, let us solve for NQ. Again, our N is 500. Our Q is 0.88. And this will give us 440. And this is greater than 5. Since both NP and NQ are greater than 5, then we can say that the sample size is sufficiently large to use central limit theorem. Let's have another activity. Am I enough? Check whether the sample is sufficiently large to use CLT in approximation. The election is fast approaching. In the recent survey, 87% are in favor of the new independent candidate. Out of 30 randomly selected voters, 27 said they are in favor of the new independent candidate. So we have here our hypothesized proportion, 87% or 0.87. Let us solve for our Q, that is 1 minus P. So 1 minus 0.87, and that is 0.13. Our N is 30. Let us solve for NP. That would be 30 times the P, 0.87, and it will give us 26.1. And this is greater than 5. Next one is NQ. That would be 30 times 0.13, and it will give us 3.9. And this is less than 5. Since NQ is less than 5, although our NP is greater than 5, still the sample size is not sufficiently large. So here is an example wherein our sample is 30, but yet it is not sufficiently large. Remember, in population mean, when n is greater than or equal to 30, we say that the sample is sufficiently large. Again, it is a different thing in a population proportion. Let us have another one. This is one of our examples earlier. Let us look for our hypothesized proportion, and that is 95%. So this is P equals 95% or 0.95. Q is equal to 1 minus P, so this is 1 minus 0.95, and that would give you 0.05. Now let's have our N, and that is equal to 250. Let us compute for NP, that would be N times 0.95, and that will give us 237.5, which is greater than 5. Now for NQ, that is 250 times 0.05, and that is 12.5, also greater than 5. Since both NP and NQ are greater than 5, then we could say that the sample size is sufficiently large. Now that you already know how to determine if a sample size is sufficiently large or not, let us determine the appropriate test for it. We know that if Central Limit Theorem is applicable, then we use z-test. Here is z-test statistic for population proportion. Recall the formula of z-test for population mean. Since we are talking about population proportion, we are going to replace this sample mean by sample proportion, and this population mean by population proportion. This is the standard deviation. And in population proportion, standard deviation is equal to square root of PQ all over N. Let us substitute this in this denominator, so we will be having P hat minus P all over the square root of PQ over N. I just added sub P here to indicate that this z-test is for proportion. Since we learned earlier that Q is equal to 1 minus P, we can replace this Q here by 1 minus P, where in this formula, Z sub P is the z-statistic for proportion, P hat is the sample proportion, P is the population proportion, N is the sample size, and Q again is equal to 1 minus P. Let me stop here. We will not compute for Z value in this lesson. Consider this as a teaser for our future discussion. For now, let us solve this problem. Solve for population and sample proportions, then tell whether the sample size is sufficiently large to use CLT for approximation. Study finds 44% of people don't consult a doctor when sick. You surveyed 25 people and found out that 12 of them don't go to a doctor when sick. Our population proportion is 44% or 0.44. For the sample proportion, let us recall the formula P hat is equal to X over N. Where n is the sample size, we have here 25, and out of 25, 12 of them don't go to a doctor. This will be our number of successes. So this is 12 over 25, and that is equal to 48% or 0.48. Now, to determine if the sample size is sufficiently large, again, our P is 0.44. Let us solve for Q. 1 minus 0.44, that is 0.56. Again, our N is 25. Let us solve for NP, that would be 25 times 0.44, and that is equal to 11, greater than 5. NQ, that would be 25 times 0.56, and that is equal to 14, also greater than 5. Since both NP and NQ are greater than 5, then we could say the sample size is sufficiently large. For the summary, here are the things that we discussed in this lesson. Take time to understand this. Now, it is time to check your understanding. Pause this video for more time. Let us answer. At least one survey has found out that 99% of students admit to cramming. You randomly ask 20 of your classmates, and 18 said they do cram. Let's look for the hypothesized proportion, and that is 99%. That's quite high. Now, for the sample proportion, again, our formula is P hat equals X over N. N being our sample size, and that is 20. 18 of them said yes, they do cram. That is the number of successes. 18 over 20. And this is 90% or 0.9. To determine if the sample is sufficiently large, again, our P is 0.99. Let us solve for Q. 1 minus 0.99 is 0.01. Our N again is 20. NP will be 20 times 0.99, and that is 19.8, greater than 5. NQ, that is 20 times 0.01, and that is 0.2. This one is less than 5. Although NP is greater than 5, but our NQ is less than 5. Therefore, the sample size is not sufficiently large. Gets? Our next lesson is identifying appropriate rejection region involving population proportion.